produce an electric field at this point. In what direction? Away from itself. So in that direction. Well, if there is a charge here, there is another one that's just like it sitting here. And it will produce an electric field in what direction? Away from itself. So there. So you have this. This vector has some to the right, and this vector has a little bit to the left. They cancel. Only the upward will survive. Only this in the y direction will survive. So that's our prediction, and the math will tell us that. And using symmetry simplifies your life. You don't have to always just do more math. So you can just skip some steps. But for now, because it's our second problem, we're going to go through the math and make sure it's there. Yeah.
So we know if the Q is positive or negative, then how do we know that it's going away or like?
Yeah, we can always assume Q is positive, and then at the end, you can always put another minus sign in front of Q. Yeah.
Oh. So for this question, you haven't like say whether it's a positive or negative charge.
I haven't, but I'm going to just assume lambda is positive for now, and then at the end we can always put a minus sign for like.
Oh.
Yeah. So whatever I get for a positive sign, for a positive charge, negative charge will just be the opposite direction.
The opposite.
Everything else, the magnitude will just be the same. So we're going to do that now, right? So I'm going to ask you, when we do dq over r squared r hat, or which form should we use for this problem?
The cube.
The cube, what? Yeah, that's not, see that vector r? It's not in the x direction, it's not in the y direction, it's somewhere in between. So this one is more helpful. This one is easier to use in this case. So that's what I'm going to use. So, before I proceed, notice that the magnitude here, r, is just equal to x squared plus y squared to the power 1/2, right? This hypotenuse, just square this, and take this square. That's the magnitude of r. So, here it is. We're going to put dE, the electric field due to just that one little bit, is going to be K times dQ. I'll put dQ over r squared. Yeah, or I'm sorry, over r cubed and then the vector r. Let's just put it all here and then go on. So again, K. What's dQ? In terms of lambda. Lambda dx, good. It's going to be lambda times dx. That's for the dq part. Now, how about r cubed? When you cube all that stuff, what do you get? Yeah, to the 3/2, right? You cube it. So you get this, right? X squared plus y squared to the 3/2. Like so? Okay. And next times the vector r. What did we say the vector r was? That's y j hat? Yes. That's dE. And now I'm going to separate it. The stuff that contains I hat, I would FOIL this in other words. Stuff that contains I hat, stuff that contains j hat. So I'm going to multiply this through. Okay? So I have dE is going to be k lambda dx times x minus, oh yeah, x and then dx, there's a minus sign, over x squared plus y squared to the power 3/2, and then I hat, right? That's the first one. Plus, multiply it through here, you get k lambda y and then dx x squared plus y squared y squared 3/2, and it's a j hat. J hat. Right. And we're going to evaluate them separately. So this is this part here. This part is the y component of the electric. This part is called EY. That's the y component of the electric, or DEY. That's the y component. This part is DE X. That's the X component. So we're going to evaluate them separately, so we don't get too long. So here is the first integral. EX is going to be the integral of DEX, which is minus K lambda integral x dx over x squared plus y squared to the power d halves, evaluated between what? What are the limits?
Negative L over 2.
Yeah, minus L over 2 to L over 2. L over 2. And you should have a good idea what this integral should be. Yes. It's going to be 0, yeah. Without doing any work. Why is it going to be 0?
They would cancel each other out.
Yeah. Well, what kind of function is this? What is it called?
Odd.
Odd. It's an odd. The bottom is even. The x here has even power. It's gonna be it's gonna be overall odd, right? Odd over even is odd. Yeah. So if it's an odd function, you evaluate from minus x to x, or minus L over 2 to L over 2, which is going to be 0. Just like the cubic function or to the third. So this is going to be 0, okay? You don't have to do anything. Don't work hard. You can use like a U substitution, and you will get a 0. Okay? It's going to be 0. Which agrees with our guess. What did we say? There shouldn't be any x component of the field. We said it should just be pointing in the y direction. Let's do the y. Dy is going to be dE y integral. This one we actually have to do something. So I'm going to just copy all that. So I get k lambda y, k lambda y. Notice the k is constant, lambda is constant, and the y is constant. The only thing that changes is the x. So these come out. What's left inside is dx, x squared plus y squared to be 3 halves minus L over 2, L over 2. This is an even function. This is even. So it's not 0. So we need to integrate this. Yes?
When we integrate that x squared plus y squared, are we treating the y squared as a constant because it's in terms of dx?
Y is constant. Yeah.
Okay.
Yeah. So it's like the number 5. Yeah. So we need to do this integral. There are 2 ways to do it,
Tricks.
or 3 ways. The first way is to look it up in a table. Second way is to let Wolfram Alpha do it for you. And the third way is you actually have to do it. All right. So which way do you want to do it?
Tricks up.
Yeah, tricks. Okay, so we should do it or look it up?
Look it up.
Look it up?
Are we allowed to look it up?
All right, so since it's the first one, okay, we can do it. What trig substitution should I use?
Tangent. Tangent.
Tangent? Yes, I like that. Yeah. You should be inspired to use tangent because when you have something squared plus something squared, what's tangent squared plus 1?
Secant square.
Secant squared. So yeah, let's do some work here. So our goal is to do this.
Like a year ago.
Right? That's the goal. So we're going to let what? X equal to what? Huh? What's the substitute? I heard tangent.
It's y tangent.
Y tangent?
What tangent theta?
Yeah, I think that's the right way. Yeah. So let's see. let's say why this is a good thing. Because eventually you have x squared plus y squared. So let's see. First of all, notice that tangent of theta is equal to x over y, right? And then, so if I have this, x squared plus y squared, I will get, let's square the x. What do I get?
Y squared.
Y squared, tan squared of theta plus y squared, which is y squared times tan squared of theta plus 1, which is what? Y squared times secant squared of theta, right? Tangent squared plus 1 is secant squared. So that's the bottom part. That's the x squared plus y squared. So that means x squared plus y squared to the 3 halves gives me what? Because at the bottom I have x squared plus y squared to the 3 halves. What does it give me?
3. Y
To the third?
cubed. Y
Yeah,
cubed.
and y to the third, right? Yeah. Because these are squared, you square root them and then cube them. So you get y cubed secant cube of theta. Okay? Yes, we're good with that. So this one is going to be this. On the bottom, I'm going to have this one. I'm going to just substitute y cubed secant cube. Okay, on the top, now we need to worry about the top. So what's dx? What do I get? I have dx. What's the differential here? What's the derivative of tan?
Secant squared.
Yeah, so I got y secant squared of theta d theta, right? So y secant squared of theta d theta. All right? Simplify that. Y over y squared is 1 over, y over y cubed is 1 over y squared. Integral. What's that? 1 over secant. What's 1 over secant? Yeah, cosine. Yeah. And then what's of cosine d theta? What's the integral of cosine? Yeah. Plus c, right? Plus a constant. We'll worry about the. Don't have to worry about the constant. Yeah.
For the limits of integration, can we just do from 0 to L because isn't it the same thing as going from negative L over
We
to
can,
L?
yeah, you can go from, so let's worry about that in a moment. I'm gonna come back to that part in a second, but yeah. Hold on to that thought and then remind me. Yes?
You can't do 0 to L because it's not linear. You have to do 2, 0 with L over 2.
Let's worry about that in a little bit. But for now, do we agree on this? I don't want to go on a, let's focus on this part, and then we'll worry about that one, that particular problem. No, I didn't put any limits. Now it's just an antiderivative. Technically, I should have plus c, but I would worry about the c. Okay, so we have this, right? We agree on this. So now what's sine theta? Sine theta, look at this. Tangent theta is x over y. Here's theta, x over y, right? Because the tangent is opposite over adjacent. So what's the hypotenuse?
X squared plus y squared.
Square root of
Square root. Yeah. So now what's the sine of theta in this case? Opposite over.
X over.
So x over this.
Yeah.
So we get 1 over y squared, and then x over x squared plus y squared squared. Here's the nice thing about integrals. You can always double check if you got it right. How do you double check if you got it right?
Derivative.
Take the derivative, and if you get this, then you know you're right. Okay? All right, so now to the question. Back to here. So for this integral, we're going to replace it by this. So to your point, this is an even function integrating from minus L over 2 to L over 2. I can just go from 0 to L over 2, but I have to double it. I have to put a 2 in front. Yeah. Is that your question? Can we double it and go from 0 to L over 2, right?
Or just 0 to L maybe?
It's gotta be L over 2.
Oh.
Yeah, to the same limit, but you can just, yeah, instead of going from minus something to that same thing positive, you can just go from 0 to 1. Because it's an even function. So, I'm going to go here, we get k lambda y. And then I'm going to plug this, right? This is going to be plugged in. So I have 1 over y squared. Let's put the y squared on the bottom. And then I have my x over x squared plus y squared. And we set square root. Minus L over 2 to L over 2. And we just have to simplify this now. No, because we didn't go from 0 to yeah. It would be easier actually if we do that. But let's continue. So I get EY is going to be K lambda over Y, right? K lambda over Y times. Let's substitute. I get L over 2. And then L over 2 squared plus y squared, square root, and then minus L over 2, and then L over 2 squared plus y squared, like so, right? And here's where why you can just double it, because what's minus minus? Plus. Becomes plus, and then you just have the same copy twice. Okay, so this becomes K lambda over Y, and then L, or twice, twice L over 2, and then L over 2 squared plus Y squared. That's EY. Really, the goal is not this line segment. So we got this result. Now the goal, okay, so this problem is finished, okay? So now to the next problem, which is to use this result to get something else. Okay. So I'm going to pause for a second, in case someone has a question. I'm really done with that, yes?
Are we looking like this much all the time for these kind of questions, or
Usually it's a little bit easier. Yeah. If it involves something, after all, it's not a math class. I would give you like and I say, feel free to use this result, this antiderivative. Okay, so I'm going to go to the next problem. Can I erase this stuff here? Good. Yes. So let's erase this, and then I will erase the board. And the next one.
Why do you get rid of the 2?
Which? Oh, why don't I get rid of the 2?
Yeah.
Oh yeah, you will see in a second. You could, definitely could. But I have one reason for leaving it there.
Tapi kalau dapat di ini di dalam ini dari aku terpal dari kuadrat itu aku sendiri bukan pintu mas mau begitu dong itu terus ngomong kenapa sebenarnya bilang bagian anak duanya dia cuma dua sampai sama warna banget mana makanya kalau tahu
Oh, that's so cute. I thought you were oh, those are black. Oh, it's black. Oh, the dark green.
So, the next one is an infinite line of charge.
I know that's what I meant. Did you ask me? I automatically
Okay? So, can I have your attention please again? This result that we got, it was for a line segment of how long? How much length? L. And right above the middle of the line. What if I want my line to become infinite? Right? Very long, in other words. What do I do? I don't want to redo all the integrals. We can just use our result. And I don't want to redo the integral again. So what happens to L?
You can
Make L infinite. So if it's infinite to the right side and infinite to the left side, then I have an infinite line. It doesn't have a beginning, it doesn't have an end. So in practice, it should just be very long. Okay? So if it's infinite, then let me write it here. We get E, EY will be. So if L goes to infinity, what's this limit? This is a constant here. The K, the Y, the lambda, constant. If L goes to infinity, what's this limit here? It is 1. This limit is 1. Okay? This limit is 1. Because you have here, when L is going to infinity, Y is negligible. What's the square root of L squared over 2? You made L over 2.
Yeah.
L squared over 2? Yeah. So you have L over 2 on top, L over 2 on the bottom. So as L goes to infinity, you get, that limit just becomes 1. So what's left?
2K.
Just this. Yeah. So I'm using, so this is just this. So that limit is 1, and you get 2K, 2K lambda over Y. But people usually write the K in terms of the epsilon naught.
Yeah.
So it becomes 1 over 4 pi epsilon naught. K is 1 over 4 pi epsilon. So we write it this way. 2 lambda over 4 pi epsilon naught Y. And so we just write E lambda over 2 pi epsilon naught. That's an infinite line. Infinite line of charge. So this result. I forget the Y, right? Yeah. So here's a line of charge. The result, we got it to be above the middle, right? If you have a finite length, there is only one middle. What if it's infinite? Where is the middle?
Everywhere.
Everywhere is the middle. Yeah. Everywhere you stop, there is infinity to your right and infinity to your left. So everywhere is the middle. So if you're here, the electric field is away. Yeah. So this way, the electric field is just away. So you can choose the origin anywhere you like. So that's, the electric field will just be away. How about if I'm here? What direction would the electric field be?
Down.
Yeah. So it's just gonna be away like that. Okay? Yeah. So, but we look only on one side of the wire, on one side of this line of charge. So I've been looking only this, right? But it's really a three-dimensional thing. What if someone is standing here? What direction is the field? Yeah, that way. How about here? That way. Here. This way. So now, let the line point towards you. Right? Here's the line towards you. And what direction is the field here? Towards us. Right? Here. Yeah. To the right, here. Left. left. So it's gonna be like this. So imagine, let me draw it this way, maybe better than the meter stick. So imagine the line, here's the line of charge. It's coming to, this circle with a dot, it means it's coming towards you. Here's the line of charge coming towards you. So in what direction is the field when you're here? All right, to the right. And when you're here, up, this way, this way, this way, this way, right? Field is like that. Up. No towards, no. Yeah, there is no like this way. Yeah, because we said there are no components this way, horizontal. So that's for an infinite line of charge. And we will use this result. It's one of those results that will stick with us for the rest of the semester. Yes?
But is it only for the positive charge or
So if you have a negative charge,
it's coming
it's
towards
going
the
to be
rock?
towards, yeah. Inward.
Yeah.
Next one is going to be a ring of charge, and then probably that's it. So a ring of charge. So let's say this line of charge has a charge Q. Somebody comes in, bends it, and makes a loop. Okay, so we have a loop. So here's the loop, the ring of charge Q, and the radius R. So here is the ring. Attempting to draw in 3D. So the ring is supposed to be here. It's supposed to look like this, right? And we're trying to find the electric field above it. So let me attempt to do that. So this is the ring. This is the radius of that ring. And we're trying to find the electric field above the ring or below the ring. Doesn't matter. Above, below, it's going to be the same. Yes.
That's not the part. Are you doing it for a positive charge?
The away? Yes.
So if it was negative.
Yes. It would be towards. Yes, correct. Yeah. I'm always assuming it's plus, and whatever it is for the plus, it will just be the reverse for the thing. Yeah. Okay. So that's the ring. Because radius R. Again, imagine here's the ring. It's at the bottom of the floor. And then we're trying to find the electric field at distance Z above it. So here is the Z axis. And so let's say this distance is Z. So Z is fixed, so I'm just above it by a distance Z, and I'm asking what's the electric field at that point, Z. So let this be. So our goal is to find the electric field here at this point. Okay? Electric field at that point. So let's take, we need to divide it into many DQs and then integrate. But here we really won't have to do any integral. It's going to be really easy. Geometry maybe they're more difficult because it's 3D, but the actual calculation is going to be easy. So here's a DQ. I'm going to take a red DQ here and ask, again, always assume it's positive charge. If it's negative, it's just going to be the reverse. So for this red charge here, in what direction is the electric field that this red charge will produce at this point? In what direction? So is it going to be away from itself? So that way. So the electric field. Remember, point charges always produce electric fields what? Away from themselves, right? Positives. Okay. Yeah. So the electric field is going to be this way. Let's take a yellow charge now. That's just like on the diameter opposite to it on this side. Here is that other yellow charge. And of course there are charges on the back. There are always opposite charges that are just oppositely away from each other, right? So I'm just taking these two because they're easier to look at. In what direction is the yellow charge, the electric field produced by the yellow charge here?
West.
West. So this way? So when you add these two electric fields, what do you get?
Zero.
The horizontal would be 0, but the top would survive. The one in the z direction is going to survive. So yeah, so the electric field will be dE for the yellow one is going to be in this direction, right? So the electric field is going to be in this direction. Only this one will survive. The z one will survive. The horizontal one is not going to be there. Those will cancel. So let me write down what dE is. dE is going to be, I just want its magnitude. I would worry about the direction in a second. dE, it's going to be what? K dq over what? Over r, right? Over r squared, sorry. Yes? K dq over r squared. I would worry about the direction in a moment. For now, just the magnitude. Over r squared. Yes or no? We're good with this? That's the electric field, right? K q over r squared.
Wait,
The magnitude, yes.
the distance is not from the point until the right point.
I'm sorry.
Like, isn't it like the slanted
The
one?
distance is from here to here. The r, this is r.
Oh, you mean? Oh, I see.
Yeah. So r is equal to what?
R squared plus Z squared.
R squared.
I will tell you in a second. That's z squared square root, right? That's r.
Yeah.
Yeah.
So because we're not worrying about distance, we're not using the RQ.
Yeah. I'm not going to do that for a reason because it's actually simpler. I don't have to do that. Yeah. But we could. But I'm going to just. We already argued that there would be no horizontal component. Only the z component is going to remain. The component that points up. So given that you have this vector, here is its magnitude. And it has a component this way and a component this way. Let's say this angle here is theta. What would, here's dE. What would dE z be in terms of dE? Be dE times what?
D times cosine, sine.
Sine of theta, yes. Would be the sine. It's this. It's dEz would be it's equal to dE times the sine of theta times the sine of theta. Here is theta. This angle here is theta. Okay. So dE, the z component, which is the only one that will survive, that's the only component that will be left, is going to be k dq over r squared times the sine of theta. Now it's time to put it all together. We substitute the numbers or the variables that are relevant. So I got k dq. What's r squared?
Capital R squared plus Z squared.
R squared plus z squared. What's the sine of theta? What's sine of theta? So here's here's theta. How do I find its sine?
Z over R.
Yeah, opposite over hypotenuse. Yeah, so z over what? Yeah, which is this, right? R squared plus z squared square root. Let's simplify this a little bit. Simplify it. You get this to the power 1 times to the power half, which becomes what? To what power?
3 over
3 halves. So I get k, and then z, and then r squared plus z squared to the 3 halves. And then I have my dq, right? My dq. Okay. Almost there. Easy. It's going to be the integral of dE c. Right. So, is k constant or variable? Can k come out from the integral?
Yes.
Yes. How about z?
Yes.
Z is a fixed point. Yeah. Z is we're a certain. Let's say we're 1 meter above the ring. So Z is constant. And then R, the radius of the ring. Yeah, that's constant. So all this is actually constant, meaning K, C, R squared plus Z squared to the 3 halves. So you just have the dq. What's the integral dq?
Q.
It wouldn't be 0.
Q.
Yeah, it would be the total charge. It's Q. And how much is the total charge? The total charge is just capital Q. Yeah, so here the integral is actually, we don't have to do anything, just Q. So it's going to be K, Q, C, over R squared plus Z squared to the 3 halves. Plus, no, it's just the total charge. So think of it this way: there is a dq here, and another dq, and another dq. So let's say you divide it into 100 dqs. What happens when you add all the dqs? You just get the total charge q. So, and then I'm going to rewrite k as 1 over 4 pi epsilon naught because that's how you would usually see it. I'm going to this k, so I get q, c, and then 4 pi epsilon naught r squared plus z squared 3 halves.
Alasan diintegral tuh apa sih?
So so you got a lot of formulas today, but the only ones really, the infinite line and the ring are the ones that we will use. The line there is just for practice mostly, just for practice. Yeah.
So we don't have a direction vector.
It's in the z direction.
Yes, everything. So we don't have to put like a hat.
You can put k hat. I'm implying it's easy. It's a z component, so it's in the z direction. Yes. Jack, I think you had.
Same question.
Oh. So E for the ring, as long as you're on the axis of the ring, you would have just the z component. Okay? How about if you're off axis? If you're here, let's say you're not here, you're here. Well, you can set an integral. You will be able to set an integral, but then you cannot do it. It would be. It's one of those integrals that you have to approximate. That's why we focus on the along the axis because it's something we can do. Off axis, you can write an integral, but then you have to approximate. Yes.
So if we had a point, let's say it's the point is at the same z point, but over we would just move the axis over there and